Do you have a lot of data? Are you having trouble keeping that data in your program? Have you used some lists in your programs lately? We are going to cover that data abstractions and lists today in this version of AP Daily Live for AP Computer Science Principles. My name is Mrs. Julia Lano from Hamilton Southeastern High School in Fishers, Indiana, and thanks for joining me today. What are we going to learn today? What will we learn? Here is what our topics are. In this video, we'll review the topics of data abstraction, iteration, developing algorithms, lists, and binary search. So we got a lot of topics to cover today, so let's get started. First up, data abstraction. For data abstraction, you should be able to represent a list or string using a variable and develop data abstraction using lists to store multiple elements. So hopefully you've used a list in your programming language, and we're going to talk about how the questions will be set up on the AP exam for lists. Iteration. So for iteration, express an algorithm that uses iteration without using a programming language. So we're going to see that in some of our questions. And yeah, you have to be able to use pseudocode or the College Board pseudocode here. For iteration, you need to be able to write iteration statements and determine the result or side effect of iteration statements. Again, a really important one as we take a look at multiple choice questions. Further topics, developing algorithms. So you need to be able to compare multiple algorithms to determine if they yield the same side effect or result. Again, good for multiple choice questions. You also need to be able to create algorithms and combine and modify existing. And lists. For list operations, write expressions that use list indexing and list procedures, and evaluate expressions that use list indexing and list procedures. For algorithms involving elements of a list, you need to write iteration statements to traverse a list and determine the result of an algorithm that includes list traversals. So you're not really going to write code. Obviously, we're going to focus on the multiple choice portion here. So hopefully you've already used your list on your create task. But for these, we're going to be looking at how lists are used in algorithms and how we can evaluate those. And binary search. That's our final topic of the day. For binary search, you will need to be able to determine the number of iterations required to find a value in a data set and explain the requirements necessary to complete a binary search. So two things, not a lot there, but it's a little tricky. We'll go over those later in this session. And the skills covered in today's session are investigate the situation, context, or task, evaluate solution options, and represent algorithmic processes without a programming language, and implement and apply an algorithm. So that without a programming language is going to come into play here. We're going to be reviewing a lot of the AP pseudocode, which is on the exam reference sheet, which you get during the exam. But let's take a look, couple more skills here. Generalize data sources through variables and determine the result of code segments. And so up for today, our agenda. So first, we're going to review important terms and lists on the exam reference sheet. So we're going to go through and look at exactly what you have during the exam about lists. We'll try some example problems, then you'll get to answer some multiple choice on your own, and a create PT tip of the day. Can't forget that. So let's review. First up, some important essential knowledge. A list is an ordered sequence of elements. For example, value 1, value 2, value 3 describes a list where value 1 is the first element, value 2 is the second element, value 3 is the third element, and so on. An element is an individual value in a list that is assigned a unique index. An index is a common method for referencing the elements in a list or string using natural numbers. And a string is an ordered sequence of characters. So hopefully you've seen a list, and obviously you had to use one for the create task. So you've worked with one in your programming language. So really today we're going to focus on how lists look and how lists are used on the exam reference sheet. So, some more essential knowledge. Data abstractions manage complexity in programs by giving a collection of data a name without referencing the specific details of the representation. Data abstractions can be created using lists. Developing a data abstraction to implement in a program can result in a program that is easier to develop and maintain. Again, all things hopefully you've realized from doing your create task. So here is some more important information, and this is what is on the exam reference sheet. So the exam reference sheet provides the notation to create a list with those values as the first, second, third, and so on items. So you can see here further down on the page on the left, you see a list and it gets value 1, 2, value 2, value 3. And then the next one shows you how to create an empty list, a list with empty square brackets. And then the last one shows you that you can assign a copy of B list to A list. So this is on the exam reference sheet. So don't forget, if you're not sure how lists work, excuse me, in the pseudocode, just to pull out your reference sheet during the test and check it out. All right, let's take a look at some more information about lists on the exam reference sheet. The exam reference sheet describes a list structure whose index values are number one through the number of elements in the list inclusive. For all list operations, if a list index is less than 1 or greater than the length of the list, an error message is produced and the program will terminate. So, your programming language that you learned in class this year may have had the index value start at 0. So, it's important to realize that for the pseudocode that's used on the AP exam, the first element of a list starts at index 1. And so I've put red boxes around this. Again, this part where the red boxes are, this is on the exam reference sheet. You have access to it. You can write on your exam reference sheet, maybe circle that to remind you that they start at index 1. And then it shows you that you can get the length. So notice the syntax for how you get the length of a list there down below on the left. And that is, again, with this AP pseudocode. So you may have done it differently in your language, but this is what you'll have to do for the questions on the AP exam. All right, some more important central knowledge. Iteration is a repeating portion of an algorithm. Iteration repeats a specified number of times or until a given condition is met. So again, we have two repeat blocks from the exam reference sheet. Repeat n times, and then you have a block of statements, or repeat until a condition is met. So those are the two repeats that you could see. And again, those are from the exam reference sheet. Moving on, some more important central knowledge. Algorithms that appear similar can yield different side effects or results. Different algorithms can be developed or used to solve the same problem. Using existing correct algorithms as building blocks for constructing another algorithm has benefits, such as reducing development time, reducing testing, and simplifying the identification of errors. So, lots of good things that we've learned about algorithms this year, and you'll be analyzing different ones and similar ones. So, those first two essential knowledge statements are really important. All right, more from the exam reference sheet. So it provides basic operations on lists, including the first one, which just simply shows you how to assign a value to a list. The next one, assign the value of a list to a variable. The next one is how you can assign a value from a variable to a list element. And the last one shows assigning an element of the list to another element in the list. So assignment statements, those are list operations that you can do in the AP pseudocode. And more from the exam reference sheet, we have insert, append, and remove. So again, you may have had these in your programming language, you may have not. But on the AP exam, you will need to know and understand insert, append, and remove. For those, insert, you can see here, you have to send it the list, you have to send it an I and then a value. So I is the position that you want to put it in, and all values greater than that are shifted to the right. So it inserts and everything else moves over. Append just adds it to the end and increases the length of your list. So you just send it the list and the value, it'll add the value at the end of your list. And remove, you send the list and an index, and it removes the element at that spot, and then everything else shifts to the left. So it's very important whenever there's remove, you need to make sure that you account for removal. So if you're iterating through a list, you remove one, then everything else shifts over, and you have to pay attention and be cognizant of your indexes. And the same is true for insert. Once you insert, everything slides over. So you need to make sure you're aware and how those operations work. All right, more on the exam reference sheet. You have a for each. So we saw the repeats, but here is a special block just for iterating through a list for each item in a list. And then there's a block of statements. So you don't even have to worry about the indexes if you're using this block. It simply says for each item in the list, and then you can use that item to do with what you want to do with every element of the list. So it's executed for each assignment of items. So every time there's an item in the list to work, it goes through that block of statements. So this is something you could see on the exam questions as well. All right, some more essential knowledge. We're almost done here. Linear search or sequential search algorithms check each element of a list in order until the desired value is found or all elements in the list have been checked. The binary search algorithm starts at the middle of a sorted data set of numbers and eliminates half the data. This process repeats until the desired value is found or all the elements have been eliminated. So, linear search versus binary search. Linear search, you got to go through every single one of them in the line. Binary search, divide and conquer, but the data has to be sorted. That's the important part of a sorted data set. So we start in the middle and we can check, oh, is it equal to the middle one or is it greater than or less than? Because it's sorted, we can use greater than or less than, which then allows us to eliminate half the data. So even if you were searching 100,000 items, you can cut that in half immediately if they're sorted and you're using binary search. We'll see some questions over that and review some more about that later. And so let's look at some examples now. So here's some example questions. First one, a list of numbers has n elements indexed from 1 to n. The following algorithm is intended to display the number of elements in the list that have a value greater than 100. The algorithm uses the variables count and position. Steps 3 and 4 are missing. So we can see that this algorithm starts out by setting count to 0 and position to 1. If the value of the element at index position is greater than 100, increase the value of count by 1. We have two missing steps, and then it says display the value of count. This is a 2-slide question. Sorry about that, but let's refocus on the question. The following algorithm is intended to display the number of elements in the list that have a value greater than 100. So notice that right now we have a counter and a position. And then we have an if statement. If the value of the element at index position is greater than 100, increase the value of count by 1. This is just an algorithm, no programming language here. So it may seem funny, but let's take a look at the next page and see what our answer options here are. Remember that we have a count and a position. We've checked to see if the element at position is greater than 100, and we have already increased the value of count by 1. All right, so here are our answer options. Which of the following could be used to replace steps 3 and 4 so that the algorithm works as intended? So step 3, increase the value of position by 1. Repeat steps 2 and 3 until the value of count is greater than 100. Notice the next answer option, increase the value of position by 1. Same option there. But then repeat steps 2 and 3 until the value of position is greater than n. So notice the difference between answer A and B. And then notice that answers C and D are even different still. Repeat step 2 until the value of count is greater than 100. Repeat step 2 until the value of position is greater than n. And then you see on C, increase the value of position by 1, and D has increased the value of count by 1. Let's go back a slide, which may help us here. Oh no, I showed the answer. Let me, right, sorry about that. We'll go back a slide. So here is the question. So back to the question, remember that count started at 0 and we're trying to count the number of elements that are greater than 100. And then position kind of tells us what it is. It's where we're at in the list. So we already increased the count by value by 1. So if we need to go on to the next element and we're repeating, so let's think about that. So we need to go on to the next element in the list, and then we also need to repeat. So let's take a look at those answer options again. So if we need to go on to the next position, then I know I can eliminate answer D because we've already increased count. So I know it has to be A, B, or C. And then when do I want to stop? Remember, I'm counting the elements that are greater than 100. I want to go through everything in my list, which was from 1 to N. So in this case, I do not want to repeat until count is a value. I want to repeat until I've gotten to the end of the list. So until my position is greater than N. So those are the two I need. Is I need to pay it. This is all about position here. So that is why the answer here that we saw a second ago is B. So answer B, increase by 1 and then keep going until we get to the end of the list or until position is greater than N. All right, long question there. Thanks for sticking with me. On to the next practice question. A sorted list of numbers contains 500 elements. Which of the following is closest to the maximum number of list elements that will be examined when performing a binary search for a value in the list? All right, so we have 500 elements. We're going to use a binary search. So remember, binary search, divide and conquer. You start in the middle, you can eliminate half of them right away. So we do one check. How many need to be examined? If we examine one number, we can eliminate 250. Well, we can keep doing that math, but there's another way to think about binary search. You can, and here is that tip on the screen. You can think about how many bits does it take to represent 500? And we talked about this in another review session. Remember, your bits are powers of 2. So the first bit can represent 1 and 0. To the next bit, right, we can get up to 4 and then 8 and 16 and 32 and so forth. So notice each one of these is a bit. So each time we put a number on the screen there, we're representing a bit. So 1, 2, 4. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits. And notice that we have 512 on there. So that means we would be able to represent all the way through 512 for sure. And so in that case, you can use that to determine the answer for binary search. So that tells us it will only take us, we only have to examine 10 elements to find a number in 500 elements. It's the worst case scenario. If we use linear search, we would have to go through all 500. So that's another way to not have to like do all that math in your head. And we've talked about bits. You should know your powers of 2. So just write them out. And right, it takes me 10 bits to represent 500. So that's my answer for how many elements will be examined in a binary search. All right, we are ready for practice. So if you need to pause the video, if you don't want to see the answer, please do. We're going to do quite a few practice questions with lists here. So let's get rolling. First one, which of the following is a benefit of using a list as a data abstraction in a program? A, lists convert all elements to strings so they can be inspected character by character. Lists often allow their size to be easily updated to hold as many values as needed. Lists prevent duplicate data values from appearing in the list. Lists are used to store all input data so that there is a running record of all user input. Hopefully you can realize some that don't seem reasonable there. If you've programmed with lists, you realize, but some of your programming languages may be different here. But hopefully you realize that lists don't convert. Look at that verb there. Lists don't do a conversion. Lists don't prevent duplicate data. You can write an algorithm to do that, but the list doesn't automatically do that. And lists, while it could be used to store all the input data, that doesn't automatically happen. So the answer here, and the one that seems most likely, is yes, it's great, and lists can easily be updated to hold as many values as needed. So that is a benefit of using a list in a program. All right, question number 2. Consider the following code segment. So you see that on the right, we have first list, which has guitar, drums, and bass. Our second list has flute and violin. And then we have a third list, which is empty. What are the contents of second list after the code segment is executed? So notice our other assignment statements there. The values from first list are copied into third list. So that means at this point, third list contains, and I'm going to kind of do some little tips over here on the slide. So after line 4, third list contains guitar, drums, and bass. So we already know what first and second list already have in them. So after line 4 there, you can see what has happened. So you want to kind of step through this code. So then first list gets second list. So after line 5, you can see that the first list now has flute and violin. Again, I would track that on the side there and write that down. Next up, we are going to run line 6. And after line 6, you can see that second list has gotten the values from third list, which we have up above. And those values are guitar, drums, and bass. So should be easy to now answer the question, what are the contents of second list after the code segment is executed? And so by tracing it line by line and jotting down, you would be able to clearly answer that the answer here is C. All right, moving on to question number 3. Here we're dealing with iteration or repeat. So consider the following code segment. What is displayed as a result of executing this code segment? You see we have 3 values. A is set to true, B is set to false, and C is set to true. The repeat says repeat until A and B. Remember that A and B means that they both need to be true for an and, that both values need to be true so it'll continue to repeat. Inside the repeat, we have C gets the value of not C. Remember, not is the opposite. So whatever C is, C gets changed to be the opposite. So if it was false, it'll be true. If it's true, it'll be false. And then B gets the value of C. At the end, it displays all those values after the repeat ends. So that's what we're trying to figure out. What will it display? So again, thinking about every pass through the loop should help you out here. So after the first pass, we see that the values of A are true and false. So that means it says repeat until. So that means true and false results in false, and therefore it will run the loop. And so inside the loop, we get C gets the value of not true, which means C will be false. And then that gets assigned to B. So B is false. So then it repeats again. So now we're ready for the second pass. On the second pass, we're checking to see if, and you can see that A is true and B is false again. So that means we keep repeating. This time, C gets the value of not false, which is true. So now B gets set to true. So now we do a third pass. And on our third pass, we have that A and B are true. So it says repeat until. So now we've reached true and true. So now it's true. So we repeat until it's true. We're stopped and it's ready to display. So now let's think about it right there. We were talking about A and B. And in order for A and B to be true, then C had to be true as well because C was assigned to B. And so that is how we come up with the answer of B. So again, use your test. You can write all over it, step through it, trace the code, whatever you need to do to make sure, and it's kind of tricky with nots and ands. So take your time, step through the code. All right, on to practice question number 4. We have some algorithms. Which of the following algorithms display all integers between 1 and 20 inclusive that are not divisible by 3? Cool, couple things to pay attention to there. And here is one of our first ones, select 2 answers. Remember, there are questions that are multi-select on this. You must select both answers that are correct. For this one, let's go ahead and take a look at what's different in each of these answers. So A and B both set X to 0. And then you'll notice that C and D both set X to 1. So Key differences there. Very important to notice those. You can use boxes or circles and write on your test to note the differences. So step 1, we obviously see differences there. But step 2 is really going to be the important part. So on step 2, we increment x by 1 immediately. So we set it to 0, but then we set it to 1, we add 1 to it. So therefore, that's pretty good because we're supposed to go 1 and 20 inclusive. So that's good news on answer A. Next up, the question says if x is not divisible by 3, that's what we want, not divisible by 3, then it gets displayed. So A seems to be good right now. So let's move on to looking at B. B says if x is divisible by 3. Well, that's totally wrong. So mark that out. We don't want the ones that are divisible by 3. We want the ones that are not divisible by 3. So B is not an option. So we can eliminate that. Next up, notice that A says we're going to repeat until x is 20. Remember that we started at 0 and we incremented by 1 first, then we checked, and then we're going to repeat. So it's important to note that we started at 0 there. So repeat until x is 20 because the line above it, it would have been 20, it would have displayed it, and then it would have tried to repeat again, but we've already done 20, so we should be good there on answer A. And answer C then also says until x is 20. But remember that answer C starts at 1. And so it took 1, check to see if it was divisible by 3 again, then do nothing, otherwise display x. So notice that too, those ifs are kind of funky. But the only differences in C and D are the until. So that's why I have those highlighted. Step 2 and 3 are the same. Step 1, 2, and 3 are the same in C and D. The difference is the until. So remember that we started at 1, so it's not the same as A, which we think is a good option because A started at 0, did the increment, then it did the display, then we said repeat. Here we are displaying and then we increment. So in this case, we would display if we would do number 20, then we would increment. So we have to go around again because we increment after the display. So that's why we need to go here. So one of the answers is going to be A, and then the other one is D because we do need to go until it's greater than 20 because of where the increment is. Again, looking for the differences in those answers can help you to find the ones that you need, and eliminating ones like B, which didn't have, which was using if it divisible by 3, then display X. We knew we didn't want to do that. So A and D, those are your options there. The list 1, is a sorted list of numbers that contains 700 elements. The list 2, is a sorted list of numbers that contains 900 elements. Let X represent the maximum number of list elements that will need to be examined when performing a binary search for a value in list 1. And let Y represent the maximum number of list elements that will need to be examined when performing a binary search for a value in list 2. Which of the following statements about X and Y is true? So we talked about this question earlier about binary search, where you can use bits to help you determine how many how many elements will need to be examined. So we have 700 elements and 900 elements. So we want to know how many elements we'll have to examine and see if that's close for 700 and 900. So remember that we can think about the number of bits it takes to represent those. So how many bits does it take to represent 700 and 900? If you write out your powers of 2 again, you'll see that 700 and 900 are both less than 1024. So that means it's actually the same. They're between 1024 and 512. So it actually takes the same amount of bits to represent those two numbers in binary, which is the quick way for you to determine that that's the number of elements you'll need to examine in a binary search. So therefore, using that knowledge, the answer is A. They are approximately equal. X is approximately equal to Y because there is not that much difference between those number of elements. The number of checks will be about the same amount. All right, we still got lots more to go here. Moving on to question 6, more repeat questions. In the following code segment, assume that x and y have been assigned integer values. At the end of which of the following code segments is the value of sum the same as the value of sum at the end of the preceding code segment? Again, we're selecting two answers, so it is a multi-select question. The code segment we're looking at is actually over here at the right, so we're going to focus on it first. So sum gets the value of 0, and the directions are, and then it says repeat x times with a repeat y times inside of that, and each time we repeat, we take the sum plus 1 and reassign it to sum. So let's set up a couple extra values here. Here's a tip. Make up values for x and y, and then see which answers have the same result for those values. So I'd pick a number like, say, x is 2 and y is 3. So if you do that, you'll notice that we repeat 2 times and repeat 3 times, which makes it happen a total of 6 times, right? So x repeat 2 times, so we do the y 3 times, and then repeat x times says do it again. We do that 3 more times. So it would happen 6 times. So really you can just look for the one that happens 6 times down below. So if we look at answer A, we assign the value of x plus y to z. So again, with my example 2 and 3, that would be 5, and it says to repeat 5 times. Not the same as what I had in my original code. Here it says to assign the value of x times y to z. Oh, that's our 2 times 3 is 6, which is what we think as the number of times that the code repeats in the original one. So that one seems good. Remember, we're looking for 2 here. So the next one, we set sum to 0. We repeat x times, and then we repeat y times. Those are not nested. It'll, again, think of your values. It'll repeat 2 times, and then it'll repeat 3 times. That's only a total of 5. So not a good option, I don't think. And then D, this time we just switched. So it says repeat y times as the outer loop and repeat x times as your inner loop. So that means 3 and 2. And so again, that will happen 6 times. So remembering that nested loops also happen if you use multiplication. That's pretty quick. But again, using actual values to think about your answers here is a great way to come up with the correct answers of B and D in this situation. Again, a multi-select problem. You must select both correct answers to get the point on these questions. All right, question 7. Oh, a lot on the screen. We're talking about a swap here. We're going to write some things down over to the side. 3 different numbers need to be placed in order from least to greatest. For example, if the numbers are ordered 9, 16, and 4, they should be reordered as 4, 9, and 16. Which of the following algorithms can be used to place any 3 numbers in the correct order? Not just these numbers, but any 3 numbers, but we can use these numbers as an example. So that's what I'm going to do here on the slide. So the first one, it says if the first number is greater than the last number, swap them. So that's what I've animated there. 4, 16, 9 is what I'd have to do, what I'd have after the first sentence. Then if the first number is greater than the middle number, swap them. So that results in 4, 16, 9 again. So that didn't get me 4, 9, 16. So I'm pretty sure A is not the answer. So I'm just going to use my numbers here and perform the operation it suggests. So for answer B, if the first number is greater than the middle number, swap them. So I come up with 9, 16, 4. Then if the middle number is greater than the last number, swap them. So I do a swap and I come up with 9, 4, 16, but still not in order. So that answer's out. Answer C, if the first number is greater than the middle number, swap them. So that's what you see there. So we end up with 9, 16, 4 still. Then if the middle number is greater than the last number, swap then. So I'm going to do that. I end up with 9, 4, 16. And we have another sentence here. Then if the first number is greater than the last number, swap them. Well, that doesn't result in anything again because the first number is not greater than the last number. So we end with 9, 4, 16. Still not what we're looking for. So let's check that last one. If the first number is greater than the middle number, swap them. All right. Then if the middle number is greater than the last number, swap them. That is true. So we end up with 9, 4, 16. Then if the first number is greater than the middle number, swap them. And that gets us our answer 4, 9, 16. So while you may have been able to determine that maybe it should be C or D because you need to do multiple swaps, that may have been a good way to look at it, but you can also just test them out writing on your test booklet. So as we can see, the answer is D. All right, we have more questions to go here, so let's move on to question 8. Consider the code segment at right. What are the values of count 1 and count 2 as a result of executing the code segment? So we have a list. The list contains the values -2, -1, 0, 1, 2. We have count 1 and count 2 are both assigned 0 to start out in this code segment. For each value in the list, we have an if else. So value, that's everything in the list. So that for each is going to go through all 5 items in our list. So the first time, value is going to be -2. So if value greater than 0, so -2 is not greater than 0, so then it's going to go to the else. So count will get count 2 will get count 2 plus 1. So we've now just increased the count. And if you look at this code, you kind of realize, oh, if the value in the list is greater than 0, we're going to add to count 1. If it's not, the else, then we're going to add to count 2. So the values that are not greater than 0 would be -2, -1, and 0. So I believe count 2 would be 3. And then the values that are greater than 0 are 1 and 2. So that should help me to determine that count 1 should be 2. And that gets me my answer of C. Count 1 is the value of 2, and count 2 is the value of 3. So kind of step through it and then maybe see if you can generalize and figure out how to get to the answer without going step by step through each element in the list. All right, we're getting close to wrapping up our practice here. Consider the code segment at right, our block of code there. What is displayed as a result of executing the code segment? This time we have a list that contains 120, 340, and 560. For each item in the list, if the item is greater than or equal to 90, we're going to display it. So again, this is a for each. So it's just going to take each item. If it's greater than or equal to 90, it'll display it. So in this case, the values that are greater than or equal to 90 in that list are 100, 300, and 500. So I believe that is what will be displayed. So our answer here is B, 100, 300, and 500. So those for eaches, if you haven't seen those before, remember it just goes through every item in the list and check. And in this case, we're going to check to see if the item is greater than or equal to 90. And if it is, we display it. All right, that wraps up our practice. And here is your Create PT tips of the day. First tip, remember your code needs to be submitted as a PDF. So your teacher can help you with those technical details. If you need help saving it as a PDF, please consult your teacher because they can help you with that portion. The code segments in the written responses must be submitted as images. So when you go to submit to the digital portfolio, you have to upload images for those screenshots. So you'll want to save those separately and make sure you have those ready to upload if you haven't done so already, because it's close. It's almost time to have that Create PT done. So hopefully you're doing well on that. But there's a couple tips for today. Again, there's a link down there at the bottom right. If you want to see more tips and instructions and videos, check that out. Check out that folder we have for you on Google Drive. You'll have plenty more tips there. And so, what should you take away from today's video? So, we talked about the topics of data abstraction, iteration, developing algorithms, lists, and binary search. So, a lot of stuff there, a lot of coding and lists. Remember to use your exam reference sheet. And if you want to review any of these topics further, check out AP Classroom for the AP Daily videos of any of the above topics. And tomorrow is the final AP Daily Live. You can join Sandy Chaika, and she will be covering advanced algorithms and programming further. So again, don't forget exam reference sheet. Please use it during the exam. Again, you may hopefully have practiced with it now, but please remember you get to use it entire time of the exam. So please reference it and check it out as you're using the exam. You see, it's not just a sheet, it's actually a packet. There will be a lot of stuff there that you'll want to take a look at. So please make sure to remember that to use that on the exam. Thank you so much for joining me today. Good luck. I know you're going to do great on the AP exam. And don't forget, final session tomorrow.